I'm Shahnawaz. We begin this lecture with the following proposition, but with before that, what we did in last lecture is that we have proved that this set pi one of x and x naught. So if x is a space or topological space in x naught is a point in x, then this is the set of all homotopy classes, say f, where this f is a path with where is f is a loop based at point x naught. So in last lecture we proved that this is a group with respect to the binary operation. So if I have two elements, say f and g, then we define their product to be the homotopy class fg, f dot g. So with respect to this operation, this is a group and this is called a fundamental group of the topological space x based at point x naught. Now we are going to prove the following proposition. So we have the proposition, and it states that if x is any path connected to topological space, then for any 2 points, say x0 and x1 in that space, their fundamental groups, that is a fundamental group of x based at x0 and x1, they are isomorphic. So let x be a path connected topological space then for all, say x0 and x1 in x, the fundamental group of x based at x0 is isomorphic. This is isomorphic to the fundamental group of x based at x1. Now a path connected topological space x is any space where any 2 points are connected by a path. So we'll prove this result here. So since x is a path connected space, since x is a path connected space, therefore for these 2 points x0 and x1 in x, therefore for x0 and x1 in x, there exists a continuous map, I mean a path, there exists a continuous map say h from the interval I to x such that h of 0 is say x1 and h of 1 is x0. So this is by definition of a path connected space. So here we have, suppose this is point x1 here and this is point x0 here. So that means we have a path between x and x0 and x1, which is given to be like this. So what we had to prove, we had to prove these two groups here, they are isomorphic. So let us define a map. So define a map, say this is, let us define this beta sub h from this space, from the group pi 1 of x naught to pi 1 of x1. Now this map, what this map does, so this takes an element here, say let us choose an element f here, the homotopy class of f. So it maps it to the homotopy class of this h f, this is dot f dot h bar. So now what this h is, so this is h here. Now h bar is the inverse of h, so this is this map. So actually this is same h but in the reverse direction. So in order to make it visible, let us draw this map here. So this is h bar here. Now what we first do, we first draw the map h, then we have a loop f here. Now f is in this group here, so f is a loop based at point x naught. So it is like this. So we first travel h, so we have traveled h here, then we travel f, and then we travel back h. So we get a loop based at x1. So this is here a loop based at x1, so this homotopy class is here. So this is a well defined map. Note that this beta h is well defined. Since for if, so let us take the homotopy class f of f to be equal to the homotopy class of g. We have to prove their h images are equal, beta h images are equal. So if this is given, this means that this f and g, they are homotopic. So this implies f is homotopic to g. Now if f is homotopic to g, we have so this or this implies this h f h inverse, so this is the product here, this is homotopic to h, so this is h inverse here, this is h g h inverse here. So these two maps are homotopic. So this further implies that so when these two maps are homotopic, so their homotopy classes are equal. So homotopy class of h f h bar, this is same as homotopy class of h dot g h bar, so this is dot and dot here. Or beta h of f is same as beta h of g. hence f is well defined. Now to prove this is homomorphism, we have, so beta h is also homomorphism. Since for if let us take two elements in this group here. Let us take these two elements in the fundamental group of x based at x naught. So we have, so beta h of, now let us compose these two elements here. This is same as beta of the homotopy class of fg. Now this is same as homotopy class of h dot f dot g dot h bar, which is same as h dot f. This is, let us take a map here, c x naught and g. Now why we took here c x naught is because of this reason. H is a map from x1 to x naught, and f is a loop based at x naught. That is why we take here x naught here. So this is g dot h bar. Now this is same as h dot f dot, now the cx naught, this is first you travel, so this is h bar here, first you travel h bar and then h, then we get a loop at x naught. So this is h bar dot h dot g product with h bar. So this is same as homotopy class of hf h bar dot hg h bar, that is beta h of the homotopy class of f dot beta h of homotopy class of g. So this proves that beta h is homomorphism. Now to prove beta h is isomorphism, we have to prove it is bijective, or we have to prove it is invertible. Now let us consider a map. Now consider a map, say beta h bar. Now this beta h bar is a map from the fundamental group of x based at x1 to the fundamental group of x based at x naught. Now what this map does, so it maps the homotopy class of g to the homotopy class by of h bar g h. Now here we have this, now this g here, this is an element here, so this g is a loop based at x naught here. So this is a loop based at x naught here, so this is the point x naught, and then we have h here, so this is x1 here, and this is h bar. So by the similar argument as above, we can prove that this map beta h is well defined. Now let us compose these two maps, beta h and beta h bar, and let us see what happens here. Now first we apply beta h, and then we apply beta h bar. Now beta h is from pi 1 x to x0 to x1, and this beta h bar is from x1 to x0. So this is a map from pi 1 x x0 to pi 1 x x0. Now let us see how this map behaves here. So now this is a map here such that beta h bar composed with, so this is composing here beta h. Let us see what will happen to this element here. So this is beta h bar of, now when we apply beta h here, so this becomes h f h bar, homotopy class of hf h bar, and when we apply beta h bar here, so this becomes homotopy class of h bar times this h f h bar dot h. So this is same as homotopy class of cx0 f cx0. The reason being h bar h is h0, since h bar h is the x0 here, cx0, which is the cornerstone loop x0. So this is same as the homotopy class of f, because this map over here, this is homotopy to f. So or beta h bar beta h, this is the identity map on the fundamental group x x0. Similarly we can prove that beta h composed with beta h bar, this is the identity map on the fundamental group based at x1 here. So that is beta h is bijective. Therefore this beta h is isomorphism, because we have proved this is invertible and hence bijective. So hence beta h is isomorphism, because beta h is beta h being a homomorphism. That is the fundamental group of x based at x0. This is isomorphic to the fundamental group of x based at x1. So when we are dealing with path connected topological spaces, we do not need to mention this point here. So let us make a note here. So for a path connected topological space, for a path connected topological space, say x, we talk about pi1 of x. So we don't have to mention these base points here. This is up to isomorphism. So from now on, from now onwards, if x is any space, say this is over path connected topological space, say x, then if we have 2 points here, x0 and x1, then obviously we have a path between these 2 points. So a fundamental group of space x based at this x0, and the fundamental group of the same x here based at this x1, these two groups are isomorphic. So after isomorphism, we don't have to mention these base points. So let us define a simply connected topological spaces. So a path connected space X is said to be simply connected if its fundamental group is trivial group. So a path connected topological space say X is said to be simply connected if it is fundamental group. Note that we don't mention base point here because we are talking of path connected spaces. So it is fundamental group is a trivial group. That is pi1 of x. So it contains only one element, and that is the constant homotopic class, the homotopic class of the constant path C x, where x is any arbitrary point in x. So this is just this set where this x is in this x. So this is a trivial group.